Well, I'm going to tell you about the short way from theoretical chemistry to analytical chemistry. Don't bother with a long name. I did my PhD with Rafi 30 years ago. I do not know if you remember this picture. From time to time, Rafi took me to conferences. This is a conference in Assisi. And occasionally he told me how science should be done. Once he told me, always do more than you are expected. And this is what I'm trying to do since this time. Actually, by the end of the PhD, I wanted to become an experimentalist. And I applied for positions of postdoc all over the world, and nobody wanted me. Now I understand why. It was very risky to take somebody who never worked one day in the laboratory for a postdoc. But I thought something is very strange. So I asked Rafi, please help me. And Rafi called his friend Karl Kompa and convinced him somehow to take me. And I don't know how he did it. He twisted his hand twice. I don't know, but this was successful, and I wanted to Karl Kompa. I started with physical chemistry research, and very slowly I moved to analytical chemistry, and now I do analytical chemistry. Now, you have to realize that analytical chemistry is different than what you are used to here in the lectures. Analytical chemistry is a science of detection and quantification of chemicals. So do not expect me to teach you something new about nature, how nature works, because this is not my task. I'm going to, I hope to impress you with some new way of measurement, new way of detection, or better abilities of detection. So now you can read the long title, which is Detection and Mapping of Trace Materials on Surfaces under Ambient Conditions using Multi-Photon Electron Extraction Spectroscopy, which you call MIS. Okay. The principle is very simple. Now, think about it. This is the principle. You take a sample, any organic material, you put it on a stage here, you irradiate it with a laser, tunable laser, in the UV. You apply some field, positive electrode above it, and connect it to a current amplifier. That's all. Now, the question is, what is the charge that you can monitor as a function of laser wavelength? Actually, if you ask a student, they will tell you nothing. You see nothing because UV cannot ionize molecules, organic molecules. If you ask professors of chemistry, and I actually did it many times, the answer will be, yes, you should see something because of multi-photon processes, but don't waste your time because this is a condensed phase. There is nothing, not enough information there. Well, surprise. This is what actually you see. This is a nice molecule. You see it here. And this is a spectrum. Photocharge as a function of laser wavelength. You see really, really many peaks. This is not done under ultra-high vacuum. This is done under ambient conditions, nothing, just in air. This is what you see. A lot of information. So what's new? Actually nothing but the fact that nobody did it before. Nobody measured the current electrons as a function of laser wavelengths. That's all. Another molecule, pyrene, for example, you see a lot of information, a lot of peaks. This is not noise. Each of these, even the smaller one, is repeatable and it's not noise. You can compare it. I did something wrong. You can compare it, for example, to the absorption spectrum of the same molecule in the solid state, which is a very difficult experiment. You have to prepare a very thin layer of this organic molecule. It's maybe the same, but much less information. You can also compare MIS to the spectrum of the same molecule in the in the solution, which is more informative, but still MIS has much more information. Now, you can also scan a surface and provide a map of the chemicals on the surface. Either you move the sample or you move the laser. You can scan the sample and get a map of the chemicals on the surface. We started studying narcotic drugs, so we measured the spectrum of cocaine, heroin, and other nice drugs. What is important to see here is that each compound has a unique fingerprint, which is very, very informative. So this kind of spectroscopy can be used for identification of the compounds. You know, it's not easy to get drugs in Israel to work with. I hope so. Well, the bureaucracy is terrible. It's very, very complicated. I struggled with it. At some point, my student told me, why do you work so hard? Give us 100 shekel. In 20 minutes, we'll bring you all the drugs that you need. Well, it didn't work like this. I was too coward to do it. The solution was I went to the police, convinced them that the project is important for them. So they sent a policewoman to my laboratory every morning with the drugs. She stayed with us all day. In the evening, she took the drugs back. She did it for 2 months. At the end, she told me that it's much much better environment. It's much better to work in the laboratories than in the police. Okay, this was the conclusion. We also tried for explosives. We found that the signals from explosives are very, very high, much more than all the other compounds that we tested before. So we thought, okay, maybe we can detect explosives in the airports. Maybe this method is better than the methods that are used today. So in order to do it, we need to estimate the detection limits, the sensitivity of the method, and the detection limits is usually in the picomole range, a few picomoles, which is much better than it's done with the ion mobility spectrometer, which is now applied in the airports. The detection limit of the ion mobility spectrometer is 1 nanogram. And here it's 1 nanomole, and here it's about maybe 100 picomole. So we wanted to see if it works. We took the device which is used in the airports for sampling the clothes and the suitcases with the swab. We use the same swabs that they use in the airport. And we wanted to see whether we can detect the explosives, very tiny amount of explosive on this kind of swabs. Actually, we were able to detect all explosives that are needed. Moreover, we are able to detect plastic explosives, which are very hardly detected by ion mobility. For example, the Semtex is a plastic explosive, and we can map the plastic explosives on the swab. This shape is actually the smearing, because this is when you try to collect the dust, you smear the explosive, so you can get the map of the, it's not needed, but to get the information where exactly the explosives are on the swab. Well, another application is detection of pesticides on fruit and vegetables. I'm vegetarian, and I like to buy organic fruits and vegetables. However, I never trust the sellers because it's so easy to cheat. So I wanted to see whether I am able to detect pesticides on vegetables to know whether it's really organic or not. So we tested it, and yes, the detection limits for pesticides on the fruits is on the order of 50 picomoles per square centimeter, which is much more than enough, which is really enough. So the method can be applied for detection of organic products. Well, if it's a new spectroscopy, then we have to compare it to traditional optical spectroscopies and see whether it's better or not. So we compared MIS to all traditional spectroscopy, like absorption, Raman, fluorescence, and so on. And the comparison was carried out for powders and also for thin films. And we took about 60 different compounds in order to see whether one spectroscopy is better than the other. But then comes the question, which spectroscopy is better? I mean, you have a list of spectra. How can you tell which is better? Of course, the first idea that I had in mind, remembering the lesson from Rafi, go to information theory and try to see which one is better. It comes out that this is not the right way. It doesn't work. People tried it before. So actually, we suggested another parameter, much simpler than information theory. We called it spectral quality density. We believe that this quantity really represents the value, the analytical value of a spectrum. And if you take this parameter, you see that MIS is much better also for powders and also for thin films. It's much better than the old traditional spectroscopy used. So let me conclude. First conclusion is that multiphoton electron extraction spectroscopy is a new general detection technology. The method can be applied for fast detection of trace amounts of many materials. MIS analytical performance is usually better than other optical spectroscopies. And finally, the way from theoretical to analytical chemistry is easy if you have some good friends on your way. You need them. I want to thank Rafi for the friendship and for the support in the time where I really needed the support and the help. And I want to thank you for your attention.